Welcome to Dr. Tarazi's math site. Modulus, remainder.
Let's recall the definition of the modulus or the remainder. So for any integer k greater than 0 and n, the integer n mod k is the remainder of the division of n by k. And that's how it's calculated. R is n mod k is equal to n minus k times floor function of n divided by k, and the floor function at x is the largest integer less or equal than x. You can see my video on floor and ceiling functions.
Example 1. N greater than 0.
Okay, I need to say 20 to find 27 mod 4. So if you're dividing 27 divided by 4, you get 6. 6 times 4, 24. So what is the remainder here is 3. So 27 minus 4 times, if you divide 27 divided by 4, you get 6.75. When you take the floor function of 6.75, it gives you this 6 here. So 4 times 6, 24, 24, 27 minus 24 is 3. Another example, 64 mod 8 is 64 minus the same formula. You get a 0. Obviously, if you divide 64 by 8, the remainder will be 0. If you do 11 mod 3, obviously is 2, because if you divide 11 by 3, you get 3 times 3, 9, and the remainder is 2. You see, the same formula is applied here, okay?
Example 2. N less than 0.
So minus 27 mod 4, the same formula, you apply the same exact formula, you get the answer to be 1. Minus 64 mod 8 is minus 64 minus 8 times floor function of minus 64 over 8, and you find it to be equal to 0. Minus 204 mod 10, so minus 204 minus 10 times minus 204 divided by 10, that's minus 20.4, and the floor function of minus 20.4 is minus 21. Now you do the math here, you get 6 as an answer.
Note.
R is n mod k is the amount R by which n exceeds its closest multiple of k.
The remainder is always positive.
So you need to remember the remainder is always possible. It's the amount n exceeds its closest multiple of k. Here, for example, 27 mod 4 is 3. Here's your 27. Now you have 4. So you have 20 here, you have 16 here, 20, 24, 28. So the closest multiple of k, okay, the closest multiple of k is 24. And how much is 27 more than 24? Is 3. That's what you get that. So same thing here, if you want to put minus 204 mod 10, here's your minus 204. Now you have the 10 here. So multiples of 10. So you get minus 210. Here you have minus 220. So minus 210 is the closest multiple of k. And then how much is minus 204 exceeds minus 2010 is 6.
Note.
In what follows, n will be a non-negative integer. So we're only interested in cases where n is greater or equal than 0.
Congruences.
N mod b equals to a is called a congruence. N and a and b are integers. N is a variable. A and b are constants. And obviously b should be different than 0 because you're dividing n by b. So you're looking at what is the value of n. If I divide it by b, I get an a. So this could be n mod 5 equals 3, n mod 11 equals 7, n mod 7 equals 9. Now obviously this one here doesn't have solutions because you can't have the remainder. If you divide n by 7, the remainder is 9. It's impossible. You can't find an n that satisfies this. Okay?
Proposition.
Consider the congruence, okay, as defined earlier. If A greater or equal than B, the congruence has no solutions. If this is greater or equal than B, this does not have a solution. If A is less than B, the congruence has infinite number of solutions, and they are given in this formula. A is one of them, and then you add plus B times T. T is an integer greater or equal than 0. For example, n mod 5 equals 7 has no solutions, because you can't divide n by 5 and the remainder be 7, because the remainder always will be less than this. So n mod 9 equals 4 has an infinite number of solutions. 4 is one of them. 4 mod 9 is 4, and then you start adding 9, like 13. You add another 9, and so on and so forth.
Example 3.
Now, this will be clear here when we do these examples. Solve the congruence. Okay, so here's what you do. N mod 5 equals 3. You start with 3, because 3 is one of the solutions, and then you start adding 5, 5, 5. All of these are solution to this congruence. Take 8. 8 mod 5, obviously is 3. If you divide 8 by 5, the remainder is 3. If you take 18, take 23. 23 mod 5. 23 you divide by 5, you get 4 times 5 is 20. The remainder is 3. See, these are all the solution which can be expressed in this formula. 3 plus 5 times t. T is an integer greater or equal than 0.
Example 4.
Solve the system of congruences. Now we have a system. We have 2 of them. Okay, we need an n that satisfies this and satisfies this. I need to find n. If I divide it by 5, the remainder will be 3. If I divide it by 7, the remainder will be 4. Okay, let's see how we can do that. So let's start with the first one. N mod 5 equals 3, as we did earlier. You create this table. N mod 7 equals 4. You start with 4, and you start adding 7. So now you look at here and see what happens here. If you scroll here and scroll here, you see that 18 will do it. Keep going. You find 53, also another solution. 88, another solution. So if you take 18 divided by 5, the remainder will be 3. 18 divided by 7, the remainder will be 4. So if you start with this, take the smallest here, and then see what happens now. See, to come from here to here, we're adding 35, which is 5 times 7. 5 times 7. The same thing here, 5 times 7. So now to write the general solution of this system, you just take the smallest, is 18, plus 35t, plus 35t. So when t is 0, you get 18, which is this one here. When t is 1, you get 18 plus 35 is 53. Okay, and so on and so forth.
Later in this article, we will define and use an algorithm to solve such problems. Example 5.
Solve the system of congruences. Now we have 3 of them. Of 3 of them, let's use the same technique we did before. The first one, second one, and third one. Okay? So now let's look at here and see which number is in the 3 columns. 53, 53, 53. See? Okay. Now, how do you get now? Okay, so it's 53, and now if you multiply 5 times 7 times 3, you get 105. So 53 plus 105t is the general solution. So after this one here will be, if you add 105 to this, you get another solution, and so on and so forth.
Later in this article, we will define and use an algorithm to solve such problems. The extended Euclidean algorithm.
Now, this is the extended Euclidean algorithm. I have a video about Euclidean algorithm that can be useful for you. Here's the algorithm, okay? N, M, positive integers, and now be careful, M has to be greater or equal than N, okay? So if M mod N equals 0, that means M is a multiple of N, all right? This algorithm will return 1, 0, N, and N will be the greatest common divisor of N and M, So 1 times n plus 0 times m is equal to n, which is equal to greatest common divisor of both n and m. Otherwise, else x, y, r, we apply now the extended algorithm to m mod n, n. So it will return this. So the output is x, y, r. R is the GCD of nm. Okay, R is the greatest common divisor, and R is expressed as linear equations of n and m. So we will use E Euclid for simplicity. Instead of writing extended, we will use E Euclid.
Chinese remainder theorem, two congruences.
Okay, here's the theorem now. For any A in Zn sub n, any B in Z sub m, there is only one x in Z n m, such that x mod n is A and x mod m is B. Here are the explanation of these symbols I use. This means for any. This means there exists only one. This means and. This means in. Now, zk is from 0 to k minus 1. Zk from 0 to k minus 1. Nm, this is important, Nm must be relatively prime, meaning their GCD is equal to 1. Relatively prime, they don't need to be prime. So for instance, 7 and 4 are relatively prime, okay? You can have 8 and 9 are relatively prime, even though none of them is prime. This is not a prime number, this is not a prime number, but both of them here are relatively prime. Their GCD, their greatest common divisor, is 1. And x mod n equals to A is the congruence. Okay, so we're solving this, we're saying that there's one solution to this system, okay, to this system.
Note:
The Chinese remainder theorem can be easily generalized to more than two congruences.
algorithm, solve a system of two congruences.
Okay. Here's how we do that. So input nm relatively prime positive integers, A in Zn, B in Zm. Make sure that m is greater or equal than n. So you order them in a way where m is greater or equal than n. So CDR is the extended Euclid for nm on nm. It returns x is equal to ADM plus BCN mod nm. Output x is the solution to the system. X in mod A is A, x mod n is A, and x mod m is B. Obviously, you can't memorize all of this. This will be given to you. You will have that.
Example 5.
Let's see this example. Two congruences. Okay. Now let's identify what we have here. Here, this is n. A comes with n. This is m. B goes with m. So m greater than n. We have all of that. What is n times m? Is 35. So now we're going to apply the extended Euclid at 5, 7. That's the same thing, extended Euclid at 2, 5. What is 2 here? So 7 divided by 5, the remainder is 2. So 2, 5. You put x, y, r here. Now, again now, 5 divided by 2 is 4, the remainder is 1, that's 1, 2. Once you get to here, so you have 1, 0, 1, which means 1 times 1 plus 0 times 2 is equal to 1. 1 is the remainder. 1 is the remainder. So now we need to go we need to go backward now. We need to go backward, okay? So this one comes here. This r does not change. R does not change. I need to find this number here, okay? So there's two ways of doing this. If I call this u, you can do it using this formula, okay? So it's y minus m divided by n floor function times x. Forget about these two because we already put them here, okay? So u is equal to y minus m divided by n floor function times x. So let's substitute. Y is 0. We're looking at the row before it, okay? Y is 0 minus m, this now here, m, and this is m, and this is n. So 5 divided by 2 times 1. So it gives you negative 2, because 5 divided by 2 is negative 2.1, and the floor function is minus 2. See, 5 divided by 2 is 2.5, and we need the floor function of 2.5 is 2, see? Floor function of 2.5 is 2. So this one here is 2. So 2 times 1 is 2 minus 2. I like to do it in a different way. What I like to do it is put, this is u here, so I need this number to be times 2 plus 1 times 5 to be equals to 1. 2u plus 1 times 5 is equal to 1. Then I can solve this simple equation. I get u is equal to negative 2. That's a lot easier. So negative 2. Now I have to go back again one more step to get to my original numbers, okay? So again, minus 2 comes to here, 1 comes to here. Now you need to get this number here, so call it v. Yeah, we can apply the same formula now. V is y minus m divided by n times x. Okay, y is 1, see, y is 1, minus 7 divided by 5 is 1 point something. The floor function is 1. So now minus 1 times minus 2, it gives you 3. I like to do it in a different way. I can do 5v minus 2 times 7 is equal to 1. 5v minus 2.2 times 7 is equal to 1. You get v to be equals to 3. So now we got all of this here. Now we apply the formula. So what's a, d, m? We have everything. A, I have it, 3. D, I have it. This one, d, is minus 2. And m is 7, you get minus 42. B, C, N. B is 4. C is 3. N is 5. You get 60. So now you have to add them. You add these two. You get 18. X is equal to 18 mod 35. What's 18 mod 35 is 18. 18 is in Z35. So this is a solution, and that's the smallest solution to this system here, okay? So the general solution is x is equal to 18 plus 35k. That's what we had before, okay? That's what we had before when we did the tables.
Example 6.
So when you see this pause and solve, I recommend that you pause the system, you pause your computer, your video, and solve the system and come back and check your answer. Again here, I need to identify my A, B, and N and M. So this is M because it has to be larger than N. With N comes A, with M comes B. Now NM is 13 times 19 is 247. So now you apply the algorithm here, you find these numbers. Now again, you just substitute ADM, BCN is 78, add them is 100 minus 112, minus 112 mod 247 is 135. So the answer is 135 plus 247k.
Example 7.
Now we have 3 congruences. Okay, we have to have solve 3 congruences. So the earlier, okay, now you have to make sure that these are pairwise prime. So which means this one with this one are relatively prime. Pairwise relatively prime. 19 and 13, that's no problem. 13 and 8 is no problem. Okay. Now, this one we just solved it in example 6. So from example 6, I get this. And then I have to apply this and this now. So I have 2. So I moved from 3 congruences, solved the first 2, and then used a solution to solve it with the third one. Okay? So now, where is my m and a and n? Okay, now, here is m, because m has to be greater than n. This is n. With n comes a, with m comes b. nm is 1976. Now you apply the algorithm, okay? And you find your answer to be 382 plus 1976k. Obviously, you can't do tables with these numbers, okay? That's why this theorem is very, very powerful.
Example 8.
3 congruences. So again, I would like you to stop, pause the video, and solve the problem, and come back to find the answer. Again, 3 and 7, 3 and 3. Sorry, 5 and 7, 5 and 3, 7 and 3. They're all prime. So basically, they're all pairwise relatively prime. Now, this 2 together, we solved it in example 5. We found this. Now I add to this one here. Okay. So now I have to solve these 2. Again, I apply the same algorithm. This is m. M has to be greater than n. And nm is 105. You do all the calculation here, you find to be equal 53 plus 105k. And that's what we found out earlier.
Note.
Now let's consider these 2 congruences here. And those are not relatively prime. They are not relatively prime, right? Because their greatest common divisor is 4. So now, the first one, x mod 4 equals to 3, which means x must be odd. The second one, x mod 8 is equal to 6. That means x must be even. So x must be odd and even at the same time. It's impossible. So this system has no solution. So that's why the condition relatively prime is very important.
Final note.
Final note, in some books you find this written in this way, okay? N mod B equals to A is written N congruent A mod B. That's how it's read. N is congruent to A modulo B. Okay, just to let you know that sometimes in some books you find it, instead of writing it this way, it's written this way. For example, a system like that would be written in this form. Thank you, and see you soon.
Thank you for watching. More videos to come. Please subscribe.